All right. Hello, everyone. My name is Zac Hatfield Dodds, and this is my talk, Stop Writing Tests. Uh, I am a little provocative with the title, but I want to say up front, I'm also quite serious. When I'm talking about these techniques, it's not that I want you to never write a test again, but I do want you to stop writing tests and think a little bit more about how you're doing that. But first, I kind of need to start with an Australian tradition that we call an acknowledgement of country. This is a picture of Canberra, where I live, and I'm currently doing my PhD in computer science. But before it was Canberra, it was Ngunnawal country, the Indigenous people of the Canberra region who have been here for something like 60,000 years, living here, studying here, working here, playing here. And they named the place Canberra, which means meeting place. And so before I get started with my talk, I wanted to pay my respects to their elders, past and present, and emerging leaders. So I'm talking about testing. And what do I mean when I say testing? It's that activity that most of us do where we try to run our code in order to find bugs in it, or just to check for regressions. When we're running our tests, we don't always want to find new bugs. We might just want to merge a feature in. And so the things that we do as part of testing are like we choose inputs to run on, we run our code, we check that it did the right thing with an assert statement, and then we repeat that however often we need to. It's important to note that this doesn't cover all the techniques that are useful for checking for bugs in our code. For example, using a linter like PyLint or Flake8 or an auto formatter like Black are extremely useful tools. I also really enjoy type checking with something like MyPy. They're great, but they're not in this talk because they're not testing. We're not actually executing our code to see what it does. And I'm going to cover about 3 parts in this talk. In the first, I'm going to talk about why would we generate test cases? Why use these extra tools instead of just doing it by hand? Then I'm going to talk a little bit about what kind of properties we can test, and then finally about some more advanced stuff I've been working on lately, about how you could fuzz your test suite or even have the test generated for you. And so my contention is that when we say automated testing, what we're actually talking about is still a surprisingly manual process. This picture is of what's called the Mechanical Turk, which Amazon now has a service by that name. But back in the 1800s, it was a system where there was this robot, this clockwork automata, which could allegedly play chess. And this was well before the first digital computers, well before transistors or even vacuum tubes. And so it caused a great stir at the time. But of course, it wasn't actually a mechanical chess player. It was a mechanism where the human hidden inside could play chess via this extended arm. And so my argument is that a lot of what we do with testing at the moment is this level of manual. What we do is we write tests entirely by hand, but in a format where we can then rerun them automatically. This is certainly valuable. It makes running the tests a second time much, much cheaper and easier, but it's still fundamentally a manual testing process. So let's start to talk about property-based testing. And to do this, I need to show you some examples. And I want to warn you that the examples I show are chosen to fit on a slide. So they're relatively simple and the inputs aren't that complicated. These tools do actually scale to much more complex examples. But in this case, sorry, David, I'm not going to try reversing a list. We're going to try sorting a list. So if we want to sort a list, this is a pretty standard problem to have, but maybe we're concerned that Python's built-in sorted function is too slow. So I've implemented my own faster version of sorted, and we're going to see how we could test it. The traditional way, and this is how I actually always start my testing, is just to try running it by hand. I like to open up Python or IPython and just call it with some inputs. And so we can see that if we try to sort 1, 2, 3, we get the correct result, 1, 2, 3. If we try to sort a list that's not already sorted, 2, 3, 1, we still get the correct result, right? 1, 2, 3, so it must be sorting it. We can then record these as test functions using something like PyTest. So we assert that sorting our list gives us the correct results in both cases, whether the input is sorted or not. And then because we don't want to repeat ourselves, we can actually turn this into a parameterized test, where we list a whole bunch of different examples of inputs and expected results. There's only one problem here, right? The reason my sorted function is so much faster than the built-in one is that it always returns 1, 2, 3. This is great because it is a sorted list. And so if we wanted to test without already knowing the correct answer, which would let us get away from this problem where we have to think up every input and output in advance, We could work out some way of finding a large collection of lists or randomly generated lists and run a test function for all of them where we don't have to specify what the correct answer is. And so this test function checks that our resulting list is sorted, right? We check that for each pair of elements, the earlier element is less than or equal to the later element. The only problem is this would actually pass for my really fast implementation. 1, 2, 3 is sorted. So we would need to add a check that not only is the list sorted, but it's the right sorted list. But it turns out that this test function will pass if and only if I've implemented a correct sorting function. And so a simpler version might have been to assert that sort list of my argument equals sorted of my argument. And if you have a trusted implementation, this works beautifully. But you can often check whether or not your code is correct without knowing how to tell whether the answer is correct. Often being able to detect incorrect answers gives you good tests on its own. And so that's the trick of property-based testing. And I want you to write more property-based tests, and that's what I'm trying to convince you to do. So the second part of the problem is that often the edge cases which cause bugs in our code are precisely the edge cases we don't know about. And this means that it's almost always the exact same test cases that we need to write because we didn't know about them, and so our code is vulnerable, that we don't know about in order to write the test. So what can we do instead? Well, you can use a tool to generate random inputs for you. And I'm going to suggest Hypothesis. Hypothesis is Python's leading library for property-based testing, and it's in fact more popular than most similar libraries in other languages. In fact, the Rust implementation is deliberately inspired by Hypothesis. So let's see what that looks like. Let's imagine that we're testing something that's a little more like realistic code rather than a sorting function. So it's going to deal with stuff on disk. It's going to have some kind of multiple steps of logic. This is the kind of thing that you might actually use every day. And it looks, in this case, a lot like Git. What we want to say is, if we check out a new branch, then the active branch is the new branch that we just checked out. And so this test function says pretty much exactly that. If we create a temporary directory, create a repository, check out new branch, and create it, then the active branch is new branch. But this is kind of a shaggy dog story. Does it matter that we're checking out the thing named new branch specifically? Do we have to have a dash in the middle of the name, for example? And so one simple way to make your test clearer is to move those specific values to function arguments. Because this test now says, if we check out with a branch name, which happens to be new branch, but could be something else, then this should pass. And so that already is a much clearer test to me. And to use Hypothesis, you can now say, instead of making a default argument, let's say hypothesis given the branch name is just new branch. So this is semantically identical. We're not changing what the test does yet. The following stuff happens. But this starts to make it easier to make a more powerful test. If we want to use the branch name in multiple test functions, we can move that out to a helper like this. And then when we start to generalize this, we can say, well, does any Unicode string work as a branch name? And when you go read the Git manual, it turns out that it doesn't. There's a whole bunch of requirements about the length of the name. You can't have white space. You can't have dashes in certain positions. Hosting providers like GitHub or GitLab often impose limits on the length of a branch name. And so we can tell Hypothesis that we only want ASCII letters in names and with reasonable bounds. And if we do this, then the test may or may not pass. We might discover a bug. And for example, in this case, if we randomly generate the name master or the name main, it would conflict because that branch already exists by default. And so let's start to revisit the body of the test function. Instead of going through this kind of shaggy dog story, we can imagine going through a similar process. So we generate random repositories as well. And we say, assuming that the branch name is not already a branch in that repository, and we check out the branch name, then that branch name should be the active branch. And that's pretty much how I described the test to you in the first place. But now the test is actually checking what I just claimed it does. All right. So what happens if you don't have a set of existing tests that you want to migrate? Do you have to learn the whole Hypothesis API? Well, of course you don't. And so I want to show off to you a thing I call the GhostTrack, which we shipped a few months ago and can save you a lot of time on writing tests. So I'm just going with the same sorting function here, right? And this will be my tests module. So if you have installed hypothesis, you get the little command line thing. And if you look at hypothesis write, then you can see there are a number of things. It can actually write your tests for you. And so we'll go through some of these examples in a minute. But the first thing to do is just go, well, if I write a test for my code, what do I get? And let's pipe that into tests.py so that we get syntax highlighting. And so what we said here is, given an input sequence, which is either a byte string that's binary or list of integers, just call the code. And this is kind of the minimal test, right? We're not checking what the code does. We're just checking that if we call it with inputs, according to the type annotation that's allowed here, then the code doesn't crash. But we could also check some more properties. We could, for example, say that it's idempotent. And that means that calling the test function twice, the second call shouldn't change the input. And sure enough, we get an error. Right, and I'm typoing this. We actually need to tell it the function, not just the module for this. And we can see that if we get the result of calling it, and then we repeat that by calling the same function on the result and the repeat result should be equal. Another test that we could do would be to check whether it's equivalent to the sorted built in. And so here we go. We get an iterable for this and a separate sequence. So we're actually going to delete that iterable because we want to use the same sequence for each. And then if we run this, we should we discover an insertion error. And so what's happened here is that we don't in fact have the same behavior because sorter doesn't take the reverse flag. But if we fix that up, then we should actually have the same behavior, right? And it looks like we can't pass that as a keyword argument. And so just through this quick process of property-based testing, we've discovered a number of ways in which the function I implemented is actually not the same as the function I was trying to re-implement. But we can look at a couple of other demos as well. So if instead of writing a thing for my particular code, we ask to write tests for the gzip module, for example, and we'll pipe that into our tests file again. We have here a number of different tests. We're checking that we can compress and decompress arbitrary data. We're checking that we can instantiate the gzip file class and so on. And while these tests aren't complete, they'll show you enough of the hypothesis API and write enough of the boilerplate for you that it's pretty easy to finish writing the test. That's all it takes in this case. So once you're using the ghostwriter, the next step, I guess, is to think about, well, what are you going to do to run this? We can, of course, run PyTest on this. Or you could use unit test if you prefer unit test. Hypothesis works well with every testing framework I know of. But you can also, let's just simplify this test suite a little. In a proof of concept, use a hypothesis backend that I'm writing called hypofuzz to actually run this a little longer term. And let me pull up a new window to open this in. So hypofuzz, instead of just running your tests 100 times each, will actually start running your tests over and over again, and it will keep running them indefinitely on a server until you tell it to stop. And at each step, it will look at the code coverage and steadily try to discover new behaviors of your code. And so this longer running process with more feedback can often end up discovering things that wouldn't have been discovered just by pure chance. In this case, we're not going to find anything because the standard library has been very well tested. Let's see. That's my talk, Stop Writing Tests. I hope you consider using property-based testing and the GhostWriter, and I look forward to talking to you in the chat.